Okay, so let's start. Is this on? Okay. So let's start. A few important announcements. One, there's a midterm next week. We'll cover everything that we're doing. Today, also on Tuesday. Closed books, we'll put online, if we haven't already, a couple of exams. Homework 2 is due on Monday. So this time, we only give you 1 day slack. The reason is that I don't want you to work on the problem set until the midterm and then not prepare for the midterm. We also want to give solutions. Two comments on this. So I know that several of you had difficulties with mostly two issues. One is SVM. So frankly, the implementation of SVM in sklearn isn't the best one, but it's working. So it's actually an important lesson. So it's okay that some of you suffer through it. There shouldn't be any problems running with the synthetic data, but depending on the implementation, especially how you represent your examples or your features, you may run into problems when you run it on the real data, which is an important lesson. So it's okay if some of you have to learn it sort of the hard way. If the dimensionality is high, memory could suffer and time could suffer. So you may need to be careful. I think that the way we gave you the feature extractors, if you follow that, should be okay. But still. Second issue is the averaged something. So as I said, we didn't tell you how to implement it. There are a couple of ways to implement it. And it's part of your homework to think about how to implement it. You can implement it in more efficient ways and less efficient ways. For example, you can implement it by keeping track of all the weight vectors. You can implement it by averaging the weight vectors as they come. You can implement it by keeping track only of the change that you make every time. These three ways are very different complexity-wise. Probably you will not see it so much in the synthetic data. Well, the first one is probably you're going to suffer from also in the synthetic data. You could see a difference in the real value data because the dimensionality is high. But anyhow, this is part of the homework. It's good for you to think about it. This is really the type of thing you'll have to think about when you implement your own algorithm or modification of an algorithm in a real-world situation. So I realize that, different implementations, you'll see different issues come up. Questions? Yeah.
Does it make sense if our average versions of an algorithm are giving lower accuracies than the algorithm?
Shouldn't happen. No, it should be better. Yeah.
What if it's like marginal? So
it could be that it's not significantly better. On which data set is it?
Worse. This is winnow. Average winnow. So my average winnow is like 1 or 2% worse.
Yeah. It could happen. I don't think it should happen though, but the results are going to be very good. On the synthetic data, the results are going to be very good anyhow. So maybe you are at the ceiling and therefore you see a little bit below. So in principle, I think it should be better, but once you're already at the, very close to the ceiling, maybe not. Other questions? Yeah.
For the average version of implementing, you mentioned in the class that's consistent with the number of consistent counts.
Yeah.
But the formula you're giving in the slides is consistent count plus 1. Because if we encounter a misclassification, we should reset the count as 0 itself.
Yeah, maybe, I don't remember, but I don't think it matters. Whether you do +1 or -1, it's going to be about the same. So, because you're going to do this consistently to all of them. Yeah, it doesn't matter. Yeah. It doesn't matter. Because we're talking here about overall, you're going to make thousands of updates. Doesn't matter. There was one question that you had that you were supposed to remind me. What was it? On? Okay, so excellent. So I forgot, you see. So in all the lectures, so the material for the exam is what I present in class. In all the lecture notes and all the slides that I put online, there are also hidden slides. I'm not expecting you to know what's there. I mean, I leave it there because they have some more details. If people are interested, you can look at it. I'm not going to test you on that. The test is on what we present in class and on additional material that you get from working on the homework. That's it. Once you start preparing, you can ask me more detailed questions on Tuesday. Okay, couple other administrative things. The recitations, because we still have problems with you entering 3401, we managed to move the recitation to Moore. So from next week, Tuesday and Wednesday next week, it will already be in Moore 216. Tuesday one starts at 6:30. Wednesday one starts at 5:30. Also, my office hours from now on to the rest of the semester, because we have faculty candidate interviews almost every Tuesday and Thursday, I'm going to start my office hours at 5 instead of 4:30. Okay, so let's start. Okay, so this is a reminder on the projects. You have to do something for the day after the exam. I know that some of you started to think about it, not all of you. We will put, I think we haven't actually put it on the web yet, but there will be a short description of what I want you to write in this one-page proposal. Yes?
Yeah, there's a question about the exam after this.
Yeah.
Do you have any tips on how to prepare for it, or?
I think you want to understand everything we've said, everything that is in the lecture notes. And as I said, we'll give you practice exams. Now, a caveat about the practice exams, this is the first time this class is being taught. So the practice exams are going to be from slight variation of this class, but still, I think it would give you an idea of what we think you should know. Ask questions on Tuesday once you see the practice exams. Okay. So, okay, where are we? So we talked about algorithms. We talked about models. The one thing we haven't talked about really is generalization, which is the key thing in learning. We want to make sure that we can generalize. So what we want to do today is give you just kind of a small window into theory of generalization. So it's not going to change algorithmically what you already know. What we will give you is an idea of how can we talk about the performance of a learning algorithm or guarantees for the performance of a learning algorithm in the future on previously unseen examples. So really, what do we want to do? We want to be able to develop a theory that allows us to think about how to relate the probability of successful learning with the number of training examples you've seen before, the hypothesis space you are using. Turns out that the size of it or some complexity parameter of it is important. The accuracy to which you can learn or we learn, and in some sense also the way examples are presented to you. So that's basically what learning theory is going to give us. So far, we only saw algorithms. Experimentally, you can see that some behave better than others and so on, but no guarantees at all. You don't really understand why learning works, when learning works, and so on. And that's what I'd like to address today. Okay, so what have we seen so far in this aspect? We talked a little bit about codifying performance, so I'm going to quickly remind you what we've seen. So we talked about learning conjunction, and in this context, this was just an example. Everything that I said about conjunction can apply to any other function you care about, but it was simple enough to explain it using this, and I'm going to keep on using this running example later today. And we talked about, for example, 3 learning protocols, right? We talked about the first protocol where the learning is active and basically asks questions. We talked about a protocol where there's a teacher that knows the truth and presents examples. And then we talked about the third protocol, which is maybe the more natural and the one we can study better, maybe not the most natural, but that's the one being studied the most in machine learning, where there is some random source of examples and someone provides labels. So we said protocol 1 was easy. We saw that we can actually learn exactly the conjunction with a small number of examples. Protocol 2 was also easy, and we saw that we can learn exactly the conjunction with a small number of examples. And protocol 3 was a little bit more involved. So we developed an algorithm for this. Again, the hidden conjunction is there on the top right, but it's hidden. The learner does not know that. The learner knows, here are examples, along with labels. How do I figure out what's the hidden function? So we gave a learning algorithm that we called the elimination algorithm. You suggested other variations of this, but hopefully everyone agrees that they're essentially the same. And eventually, we found a conjunction. And that's the conjunction that we found. And you can look at it and contrast it with the hidden one. So we asked if that's good, how well are we going to do in the future, given that this is what we've learned? And we agreed that we will make mistakes in the future. We don't know when, we don't know how many, but we are going to make mistakes, and you also understand exactly what kind of examples you're going to make mistakes on. So the bottom line of what we said is, with the given data, we only learn an approximation of the true concept. We don't know how many examples we need to see to learn exactly. Maybe we'll never learn exactly. Maybe we'll learn exactly in the next example we'll see. We did know how many mistakes we're going to make. So at that point, we quantified things in terms of the number of mistakes, which is also a useful way to quantify it, but not as useful as what we're going to say now. And the reason it's not as useful is that you don't know what's going to happen in the next example. Right? You don't know whether the next one you're going to make mistake on or not, and you have no way to estimate what's the probability that I'm going to do well next. In addition, we'll be able to quantify a few other things and really understand the generalization better. So once we finish this example, we said that there are two directions we can proceed. One of them is talking about mistake-driven learning algorithm, which we did. And today, we're going to talk more about this probabilistic intuition that we kind of developed last time. So this is just a reminder of terminology because I'm going to use it in the rest of today. You already know everything. We have an instance space that we typically call X. We have a concept space that we often call C. Today, we're going to make a distinction between the concept space, which is the set of all functions where the target function could be, and the hypothesis space, which is the set of all functions the learning algorithm is free to use. H and C, capital H and capital C, could be the same space, but they don't necessarily have to be the same space. We've already seen that before. And then we have a collection of training examples. And our goal is to determine a hypothesis H in H such that H of X, the prediction of the hypothesis, is equal to the prediction of the target class. Yes? So, for example, you could learn conjunctions, but you will not use the space of conjunctions, but rather you will use the space of linear separators. Right? That's what we've done. In fact, in your homework, you're doing it in the first part. I actually told you that the target function is m out of n, or k out of m out of n, but I didn't ask you to learn it into this form. It's going to be hard. Instead, you learn it into a linear function. So H, space of all linear functions of some dimensionality. C, space of all k out of m out of n functions. Okay? So was your question, why do we want to do it, or whether it happens?
I guess my question is see what we're looking for. Like we see the possible functions that we could possibly come up with, like the linear classifier versus
No. So C is the set of all hidden functions, and your hidden function is one of them. Example in the homework is C is the class of all function of the form k out of m out of n. If you read the text of the homework, we describe what is the hidden function. We didn't tell you exactly the k and the m and the n. Well, some of them we did. So you don't know which is the function, but you know that the function, we've written it as k out of m out of n. But we ask you to learn a linear function. So this is your H. In the decision trees, homework 1, same thing. I wrote this function. In fact, you don't even know how I wrote this function. It was a simple set of rules. You learned it as a decision tree. That was your H. And you also learned it as a linear function on top of small decision trees. That was your H. So H and C may not be the same, but when we talk about theory, I have to name them because we may want to say something about them. So that's an important issue. So everyone is clear about this? These are spaces of functions. They may or may not be the same space of function. Okay, so, but our goal is to find H that is identical to C, and then you can think about it. Do we want H of X to be equal to F of X for all X in S, where S is here, the set of all training instances? Is that what we want? Probably not, because that's rather easy to do, in principle at least. What we want is this. for all x in the instance space, because that means that we'll do well also in the future. And that's going to be hard to do without making additional assumptions. And the additional assumption that we're going to make, that I highlight here, is that the training instances are going to be generated by a fixed distribution, unknown but fixed, that we call D. And when we determine H, the hypothesis, we're going to assume that the instances are also going to be drawn according to the same distribution. We have to make these assumptions because otherwise there's no chance we'll be able to say something about future instances. They can be very different from what you've seen in training. So this is a sensible assumption. Okay, and once we talk about this assumption, you can take this conjunction along with this missing or superfluous x1 and think about what does this assumption mean about the type of mistakes we're making. So this is the intuition that we want to carry with us to understanding the theory. So we've seen many examples drawn according to this distribution D. Since I'm doing everything now in the context of this conjunction, just to make things concrete. Since in all the positive examples that we've seen, x1 was active, it's very likely that it will be active also in future positive examples, right? Because we are sampling all the time from the same distribution. If not, maybe it will be active also in negative examples, but given that we've seen a lot of examples already, it's likely that it's going to be active in a small percentage of the examples that are negative, so the error that will incur because of it is going to be small. That's the intuition. Now, the error that we measure is the probability according to this distribution, x is taken from D, of f of x being different from h of x. Now, notice that this is a Boolean predicate here, right? It's either this is true or it's false. I wrote it here as a probability. You could have written it as an expectation. It's the same thing when we're talking about a Boolean thing. So essentially, you can think about it as counting the number of times weighted by this distribution of this happening. And this is the picture that you can see. So the big rectangle here is the space of all instances that we have. The interpretation of this picture is the blue circle here is F. So inside it are positive examples of F. Outside it are negative examples of F. The red circle is the hypothesis H. So inside it are positive examples of H. And outside are negative examples of H. So this symmetric difference here is where we make errors. Now, this is a little bit misleading, this picture, in the sense, in two ways. One is, don't think about the area as indicative here. It's a distribution. There is a distribution that kind of goes out of this board into U. So some examples are weighted more than others, but I don't know how to draw this, so it looks flat. Yes?
Would it be correct to say that f is the function that explains the true relationship between x and y, and h is our approximation?
Exactly. F is the truth. This is how the examples were labeled. This is our target function. H is what we learned. And what we want is we want to minimize these differences. The areas where H and F disagree. Now, so one misleading thing about this picture is that I don't show the distribution D, just the area. Another misleading is that it doesn't represent exactly the picture for this conjunction. What should I have done to better represent the conjunction case? Yes? H is a subset of F, because we will not have mistakes like this, where H is positive and F is negative. In general, we will, but in this specific case, because of the conjunction, actually, it will look like this. Okay? So this is something you want to make sure that you got. This is the special case of the conjunction. So now, let's see what can we do. So it turns out that we can actually analyze in an exact way. And again, I'm giving you an analysis for the conjunction case, because I think it's clear and concrete, and then we'll generalize. So what can we say about this? So let's Z be a literal. Literal is a variable, one of the xi's. I'm going to denote, so it's going to be a little bit of probability. If some of you are not very comfortable with probability yet, hopefully you'll be convinced by this nevertheless. So I'm denoting by P of Z the probability that under my distribution D, I get a positive example, and Z is false in it. Okay? So think about what we had before. Positive example and X1 is false in it. So the probability that this happens is P of Z. Now, I want to argue, so these are exactly the cases where we're going to make mistakes, right? If X1 was false in a positive example, we would make a mistake. So the error, therefore, that we're going to make, the error that the hypothesis H is going to make, is the sum of all those literals in H of P of Z. Now, it could be overlapping reasons, but it's definitely not more than that, because every variable is going to cause us to make P of Z error. Now, P of Z is also the probability that a randomly chosen example is positive and Z is deleted from H. Right? Because if I get positive and Z is false in it, our algorithm before would have deleted it. It would say, well, it cannot be in H. Right? Therefore, you would agree that if Z is in the true function, in the target concept, P of Z is 0. Everyone agrees? None of these correct things, like X3, because I know it's correct, it has to be in the conjunction, P of X3 is 0. It cannot be false in a positive example. Okay, so now my claim is, and you already agree with this claim, nevertheless I'm going to say it, is that H is going to make mistakes only on positive examples. You can justify this to yourself. I'm going to justify it here again. A mistake is made only if a literal Z that is in H but not in F is false in a positive example. Right? In this case, H will say that it's a negative example, but it's actually a positive example. This is the only type of mistakes we're going to make. Okay, so now that you're convinced of that, which you were convinced of that, I think, already a couple of weeks ago when we talked about it, we can move to the analysis. So P of Z is therefore also the probability that Z causes H to make a mistake. Now, as I said, there could be overlapping reasons for making a mistake, right? It could be that I had another X17 that was similar to X1. So sometimes maybe there'll be an example that is positive and both of them are false at the same time, or just one of them is false and so on. So there could be overlapping mistakes, but I don't care about it. So, okay, so now that we know what's P of Z, I'm going to say that Z, a literal Z, is bad if P of Z is greater than epsilon over n. What is epsilon? Epsilon is some error that I'm willing to incur. Yes?
So when we say Z is in the hypothesis H, is that Z is
No. Z is one of these guys, is one of the x1 up to 100. So for example, x3 is in the hypothesis. x99 is not. That's what I mean, okay? Okay, so now that we know what P of Z is, let's assume that you're willing to suffer error epsilon. I'm going to say that Z is bad if P of Z is greater than epsilon over n. Why do I call it bad? Because these are the Z's that are going to bother me. These are the Z's that are going to cause me to make mistakes, especially if they have high probability. So a bad literal is one that is not in the target concept. So it's not x3. It could be x99 or x1. Because we know that P of those that in the target concept is 0. So it's not in the target concept, but nevertheless, it has significant probability to appear false in a positive example. So these are going to bother me. So I call them bad. Now notice that if I have no bad literals, which means all literals with positive P of Z, the probability P of Z is less than epsilon over n, then my error is going to be less than epsilon. Because the error, as we agreed, is the sum over all these literals, P of Z. If all of them are less than epsilon over n, I'm summing over less than n things, so it's going to be less than epsilon. So that's the case if we don't have bad literals. What if we do have bad literals? What does it mean that we have a bad literals remaining in my hypothesis? It means that I did not eliminate it as I was learning, right? It stayed. For example, x99 I did eliminate. x1 I did not eliminate. So if there are bad literals, it means that it survived my learning process. What is the probability that a literal survived my learning process? So the probability that it survived one example is 1 minus P of Z. Because with probability P of Z, it would appear false in a positive example, I would eliminate it. So with probability 1 minus it didn't happen, I didn't eliminate it. So it's 1 minus P of Z, which is less than 1 minus epsilon over n. Now, I observed many examples, not only one, and they are independent examples. So the probability that it survived m examples is just this times m. Okay? Independent things, I just multiply the probability. Think about two coins, two independent coins. The probability that you'll get head in both of them is a quarter. A half times a half. This is exactly the same thing. So the probability that it will not be eliminated by m examples, independent examples, is 1 minus epsilon over n to the m. And so this is for one literal. But there could be n bad literals. The probability that some literal would survive all my m examples is bounded by n times this. There could be up to n things. So it's basically bounded by the sum of all these events. So that's it. So that's the probability of the bad things that could happen. What do I want here? I want that the probability that bad things could happen will be small. So I'm going to say, you know what? I want that the probability move. Okay. We want this probability to be small. Say I want this to be bounded by delta, another small number. Okay? So that's what I want. I want that the probability that some literal survives all the m examples, which I convince you is n times 1 minus epsilon over n, bounded by n times 1 minus epsilon over n to the m. I want this to be less than delta. That's it. Now we are done. From this, what I want is I want to isolate M and tell you how many examples do I need to see so that this will be small. Now, let's see what we have here. Delta is a fixed number that you choose. Let's say you want confidence of 90%, which means delta is 10%. Epsilon is another number that you choose. You want your error to be less than 1%. N is given. It's part of the problem. I have n literals. So the only thing that you can control here or change is M. So now, given that this is our requirement, you can isolate M from here and tell me, okay, if you want this epsilon, this delta, choose M to be this, and you'll get it. Yes?
So, if n is really large, how can this probability be larger than 1?
If it's larger than 1, then it's always, it will never happen. Right? So don't choose this delta and epsilon. But yes, this could happen. So, okay, so in order to isolate M from here, I'm doing a little bit of algebra, just 2 steps of algebra. This is the first step. The first step is I'm using an inequality. It's always true, you've seen it in calculus, but you don't remember, that when x is positive, 1 minus x is less than e to the minus x. Okay, so I'm going to replace this 1 minus x here. X is epsilon over n. I'm going to replace it by e to the minus this. So rather than requiring this, it's sufficient to require that. That's all I did. I replaced the 1 minus blah with e to the minus blah. So now it's easier for me to isolate M from here. You can take log, take natural log, and divide by something, and that's what you'll get. You'll get that you want M to be greater than this. You do the algebra and figure it out. It's really simple, but what I want to highlight here is that it makes sense. It makes sense because it's inversely proportional to delta. Okay, so if you want to be very confident, you're going to pay more examples. It's inversely proportional to epsilon. Again, if you want small error, you're going to pay, see more examples. And it grows with n, which means if the dimensionality is higher, you're going to pay. You're going to have to see more examples. Okay, so basically what did we proved the first generalization theorem, and also the simplest that we can prove. We showed, what we proved is that if we see enough examples, these many examples, we guarantee that the probability of failures, error greater than epsilon is missing here, is small. It's less than delta. Okay, so just to summarize what we've proven, this theorem, we said if M is as above, with probability at least 1 minus delta, there are no bad literals. Or, equivalently, if M is as above, with probability at least 1 minus delta, the error that we're going to incur is less than epsilon. Everyone is clear about what we showed? So that's really the fundamental generalization theorem. I proved it only for the case of conjunction. As you'll see in a few slides, exactly the same thing can be proved. Also the same math can be proved in a more general case. But this is a concrete case. Now you can plug in numbers, which I did here just to give you some intuition. The numbers end up to be large. So if you want delta to be 0.1, your confidence, epsilon to be 0.1, and n is 100, you need to see 7,000 examples. Really, these are very, very loose upper bounds. You can probably do it with a lot less, but it gives you some idea. One interesting thing to point out is that it scales logarithmically with 1 over delta. So you can change delta significantly without changing m so much, but it scales linearly with epsilon, so that will change it more. And I give this example here when I change delta from 0.1 to 0.01. Okay, so So let's move one step up and see what we are doing here. So we have an instance space, X. We have an output space, Boolean classifiers plus or minus 1. We are making prediction with these functions, H from X to Y. We have an unknown distribution, D. And we have a set of training examples of size M. Given that we have this, we can define two concepts. One is the true error, the probability over D that H of X is different than Y. And the empirical error, which is what we see on our training data, the probability over S that H of X is different than Y, which is basically counting the number of mistakes. Notice that for a reason, instead of I now say H of X different than Y, rather than H of X different than F of X. So empirical error, sometimes you'll see it as observed error or training error, and so on. So once we have this definition, we can ask the following questions. We can ask, can we bound the error that we care about, error D, as a function of error S? If we have this notion of function space C and H, we can ask, is C learnable? That is, if you tell me that your hidden function is in C, can you even learn functions in this function? I'm going to make this a little bit more specific. Maybe M is going to be infinite, so I cannot learn. The number of examples I need in order to learn is going to be infinite or exponentially large, then I would say that I cannot learn these functions. So this formulation allows us to ask these questions. Okay. So the reason I made this distinction here, what is it? I didn't write F here, but I wrote Y, is because it's quite possible to imagine a scenario where you don't know what is the function space C. You don't know what kind of functions you're after, but you have the label data. So I just want to talk about H of X different than Y rather than H of X different than F of X. I don't know if F exists. Yes?
I wanted to see if I was understanding correctly. So basically the bound that we find on M, if we have that many, sufficient number of examples, we should be able to learn the function space. Correct.
So whether M, so in a second I'm going to make a distinction of whether M is polynomial or exponential, and I'm going to say that if M is exponential in the complexity parameter of the problem, let's say N in this case, I don't count it learnable because I will need too many examples. And if M is polynomial, then I count it as learnable. But the first step, in order to be able to say this, I should be able to quantify M as a function of the other things. Okay, so what are really the requirements of learning? This is, again, conceptual. So hopefully what we've done so far convinces you that we cannot expect to learn a concept exactly because in generally, once you see a set of examples, there could be many functions that are consistent with training data. This is something you know already from the first example that we've seen for the badges. So, and potentially, therefore, unseen example could take any label. So basically what we agree is to misclassify uncommon examples that do not show up in the training. So that's one thing that we cannot expect. We cannot expect to learn things exactly. Second, we cannot expect to learn a very close approximation to the target concept because sometimes, even if we make this assumption on same distribution, it so happened that the sample that we've seen is not representative. Right? There could be a probability that this happens because everything is probabilistic. So therefore, with these two together, the only realistic expectation of a good learner is that with high probability, it will learn a close approximation. So the close approximation means the error that we're going to incur. This is going to be the epsilon. The high probability is going to be my confidence that this is going to happen. So this is going to be my delta. Okay, so there are two sources here. One is you will probably not learn exactly. That's epsilon. And even having a close approximation may not happen. But I hope that it will happen with high probability. So with this, we can have a definition that is called probably approximately correct. And now you can see why probably delta and approximately epsilon correct. I'm just summarizing this, and this is the definition. So in probably approximately correct learning, one requires that given a small parameters epsilon and delta, with probability at least 1 minus delta, with high confidence, a learner produces a hypothesis with error at most epsilon. And really, it should be clear that the reason we can hope for this is this consistent distribution assumption. The fact that what you've seen in the training is sampled from the same distribution of what you'll see in the future. So this is a quantitative definition of what I just said. So I'm going to put some parameters. So we have a concept class C defined over instance space X, a learner L that makes use of a hypothesis space H. I'm going to say that C, now C is a class of functions. I don't know which one is the hidden function, but I know that it's coming from C. So I'm going to talk about C as the learnable class. And I want to be able, by being learnable, I mean that any function that comes from this C, I will be able to learn. So C is PEC learnable by algorithm L using hypothesis space H if for all functions in C, for all distributions D over my instance space, and for some fixed epsilon delta parameter that you choose, my algorithm L, given a collection of M examples that are sampled independently according to this distribution, can, with probability at least 1 minus delta, give a hypothesis H that has error less than epsilon. And it's doing it by using M examples where this M is polynomial in the important parameters. So in this case, the important parameters are 1 over epsilon, 1 over delta, N, and the size of H. So that's going to mean for me that I can learn the function. Now, two comments. One is the top part here only talks about will my number of examples M be polynomial, be tractable. I didn't talk about how long it's going to take me to learn. So I can have an addition to the definition. Instead of PEC learnable, I would call it efficiently PEC learnable if this also happens in time that is polynomial. That's one thing. The second thing is you can notice that everything we are doing here is worst case. For all functions in F, for all distributions, and so on. And you could say, why don't you constrain it? Why don't you just limit to some distributions? Maybe I can only learn over uniform distributions or some other distributions. Two reasons. One is, it turns out that everything you can do, it turns out that this is a robust distribution in the sense that you can change it many ways. You can restrict this or that. It doesn't really change a lot of things. What you can do in one case, you can also do in the constraint cases. What you cannot do in the constraint cases, in the general cases, you can probably not do in the constraint cases. And I'll point out at least one case like this. So it is a robust distribution, a robust definition. A little bit of history. So in fact, it's actually an interesting time in history to talk about the history because machine learning before the mid-80s was a completely experimental field. People had no idea what they were doing. They were inventing algorithms, running them on little data, and saying, oh, I got it right, or I didn't get it right. So that's a good algorithm, that's a bad algorithm. Now what people are doing is the same thing, only they are running it on a lot of data. So in the middle, between the mid-80s and about 5 years ago, people understood learning, developed a lot of theories for when learning works, why learning works. Some of these had a lot of implications. Some of these theories had a lot of implication on which algorithms we're running today. And I'll point this out in the next couple of weeks because we're going to talk about algorithms that are immediate derivatives of theoretical questions. But basically, we developed this pack learning theory and other theories that really explain when and why learning works and what does learnability depend on. So this started with Les Valiant, that in '84 wrote a paper called Theory of the Learnable. And then it was also built on a lot of statistical work done by, in Russia by Vapnik. And these together, these two lines of work together, actually gave us a lot of understanding today, with a lot of other followers, of course, a lot of understanding for the theory of learning. Okay, so what can we say now? So what I'm going to do is I'm going to phrase a theorem that is equivalent to what I did in the conjunction, just slightly more general, that puts a slightly more general face on what we've done so far. So I'm going to prove the following claim, or claim the following claim. The probability that there is a hypothesis H that on one hand is consistent with all my M examples, so it's good. As I was learning, I got something that is consistent with all my examples, and at the same time is not good enough. Its error is greater than epsilon. The probability of this, what do you want this probability to be? Small. You want this to be small, right? Because this says, number one says you've learned and you were happy. Number two says, nevertheless, your error is large. You don't want this to happen. You want this to happen with a small probability. So, okay, so now we lost the animation, but we can still read it. So the probability that 1 and 2 happen is small. It's 1 minus epsilon to the m. So it's exponentially small in m. Okay? Which is what you want, right? So you choose epsilon 0.1 as m grows, which means as you are consistent with more and more examples, the probability that bad things are going to happen is exponentially small. But it's not only 1 minus epsilon to the m, the size of the hypothesis space comes in here. So this replaces the n that we had before for the conjunction. The argument is exactly the same. I'm not going to repeat it. You will read it. It's exactly the same. We are consistent with the chance that we're going to be consistent with that our example will survive. A bad example will survive. One example is 1 minus epsilon. The chance that it will survive m examples is 1 minus epsilon to the m. But this is for one function. Because we have size h functions, my bound is going to be what I have here, which is size of h, 1 minus epsilon to the m. Okay? So it's really the same argument from before. And it still leaves the question, okay, so what is m? That's what I care about. So what I need is I need to take this and isolate m from it. But we've done this before. It's the same algebra that I did before, only that to make sure that you understand what I'm doing, I changed the order of the algebra. Before, first I used this inequality and then took log. Now I'm first taking log and then uses this inequality. Same thing, but it will hopefully give you an idea that you know what's happening here, and you get this. So this is the general bound, not for conjunction. And what you see is exactly the same thing. It's inversely proportional to epsilon, inversely proportional to delta, and grows with the size of the hypothesis space, or better, with the size of the log of the hypothesis space. With the log of the size of the hypothesis space. So that's it. So now we understand what does learnability depend on. If we see these many examples, and this number is polynomial, we can learn. Okay? Which means what we want is that the log of h is going to be polynomial. According to Peck theory, under these conditions, you can learn. So at this point, you should complain about one thing. And it's written in this square. One word should bother you. Choose a word in this yellow square. Consistent, okay. Consistent bothers you. Why does it bother you? Maybe it's too strict, right? So you really wanted us to be consistent with all the training data, right? And only under these conditions we proved everything that we proved. And you want to relax it, right? You want to say, well, let's be almost consistent. So it's going to come, but for now, let's keep consistent. Let's assume that our learning algorithm is so good that when you give it m examples, it's actually completely consistent with the training data. Zero mistakes on the training data. So what we've shown is that with zero mistakes on the training data, we're going to generalize. And what you want to extend it to is with a little bit of mistakes on the training data, we can also generalize, which we'll do. But it's good that that's the word that bothers you. Okay. So another thing that you should think about here is, again, size of hypothesis space, which we talked about several times, because what you can see here is that you want h to be small, right? Because the number of examples I need to be good at scales as the size of the h. So I want small h's, so I will not have to see that many examples, right? On the other hand, what's the other hand here? If h is going to be too small, what will happen? There's no chance I'll be consistent because my hypothesis is not expressive enough to be consistent with the target function. So there is a trade-off here. On one hand, I want to be expressive enough. On the other hand, I want to be small. And this is exactly a trade-off that we already talked about. Okay, so let's stop for a second. Why should we care about all these things? We can just run algorithms and see what happens. So we now have the beginning of, to be fair, a theory of generalization. So we know something about what are the important complexity parameters. We know that size of h is important. We understand the dependence of the number of examples on the size of the hypothesis class. And as you will see next week, this is really, really important because it actually dictates how to develop new learning algorithms. It's not only a theoretical understanding, it has real practical implications. Also, so that's the key thing. Second bullet, we also have a generic procedure for learning that is guaranteed to generalize well. What is the generic procedure? Take a sample of size m examples, develop an algorithm that is consistent with it, everything is going to be good. Of course, provided that m is large enough according to what we said. So that's a generic learning algorithm, and you know the future is going to be good if you do it. Of course, you still care about this consistent word. So we developed the theory of consistent learner. I just said it, I'm not going to read it again, but it says exactly what I just said. If you take m examples, this is this square rectangle here. You take m example, you find h that is consistent with it. If m is large enough, and it says how large it should be, everything is going to be fine. Now notice that there are, for conjunctions, we did this directly. We didn't have to do this directly because I could have just do the general case and then plug in the size of conjunctions as size of h. It will give you about the same answer modulo some constants. Okay, so now we can give a lot of examples. One example is this conjunction where I plug in the size of the space of conjunction, which is 3 to the n, into the general bound. And what you get, as I said, is exactly what we got directly for the conjunction modulo this constant. We get ln 3 here and stuff like that, which you didn't have before. But really, it's the same thing. So that's one thing. The other thing with why should we care is that we have now tools to prove that some hypothesis spaces are learnable and some are not. And I'm going to give just one example. So here's the function class. It's the function class of KCNF. What do I mean by KCNF? I assume half of you know. CNF is a conjunctive normal form. It's a function that looks like this. It has a lot of disjunctions. This or this or this or this or that. And it takes all these disjunctions and conjoin them. So it's this or this or this or this, and this or this or this or this, and this or this or this. So what I show here is a conjunction. This is a conjunction of all these disjunctions. This is an OR sign, this is an N sign. Why is it called KCNF? Because each disjunction here has up to k things in it. Typically k, if I have n variables, k is going to be much smaller than n. Otherwise, if I do not limit it to k, then any Boolean function can be expressed this way. So I want to show that this very expressive class of functions is actually PEC learnable. So this is more expressive than all the functions you're playing with in the homework. Not as expressive as decision trees, because decision trees is a universal representation. So what do I need to show? I need to develop this consistent algorithm, or Occam's algorithm. Draw an example of size, a set of examples of size m, find a hypothesis that is consistent with it, determine sample complexity, m. If m comes to be polynomial, in the complexity parameter, which is going to be n, epsilon, and delta, then I'm going to be happy. So the first thing we're going to do is a little bit of combinatorics to convince you that size-wise it's okay. So I'm going to count how many functions of this type are there, approximately. And So think about it. So I have a lot of disjunctions, and then I choose m of these disjunctions and put them here and conjoin them into my function. How many disjunctions are there of size k? Something like that. So actually there are 2n variables that I can choose because I could have negations also. Right? So I have 2n variables and I have to choose k of them. So it's something like 2n choose k or 2n to the power of k, which is about that. So I'm writing it here as 2n to the power of k. Okay? And then, so I have 2n to the power of k disjunctions, and then I have to conjoin some of them. How many ways do I have to conjoin some of them? All subsets. I can take a subset of these disjunctions and conjoin them. I can take another subset, conjoin it. So how many subsets it has? 2 to this. So if I have a set of size S, there are 2 to the S subsets of it. So altogether what I get is 2n to the k, which is the number of these guys, 2 to this number. And then I want to take log of this, because we said that we care about the log of the size of the hypothesis. So what I'm going to get is something that is order of n to the k, which means it's a polynomial. That's why I kept k fixed, so it will be polynomial. So everything is fine in terms of this. So sample complexity, we're good. We are polynomial in n. Algorithm. Can you develop an algorithm that learns these functions? Ideas? Oh, wow. Yes?
I have a question, actually.
Yes.
Why is it 2n? Could you repeat that?
Because I have 2n variables, really. I have, for each variable, I also have the negation of the variable. And in principle, I can put in a disjunction both variables and their negations. Suggestion of how to learn this class of these functions? So I have this or this or this or this, and this or this or this or this, and this or this or this or this. How do I learn this? It's a tricky question, because it's hard to learn it directly this way. But you have a trick. Yes?
I've got them that trick, but it's where you take the and or the flip them during the.
You can do this. It's not going to save you here. So it's a good start, but it's not going to save you, because then you will get ors of n's.
I was thinking that way, maybe then we can break it into small problems and solve all the conjunctions.
Yes, you can break it into small problems, but when you get an example, the problem here is that if you get a negative example, it means that one of these disjunctions is negative. Right? Think about it. If you have outside you have a conjunction. If you are negative, it means that one of these components is negative, but you don't know which one. So you have this credit assignment problem. Which of my components should I blame for the negativity of this example? So that's not going to work directly. But the trick, and that's something that we already talked about multiple times, and you'll see the importance of it here too, is we can change the feature space. Instead of working in the space of my features, I'm going to invent new features. What is the set of features that I'm going to invent here? Set of all disjunctions. So if I start with x1 up to xn, I'm going to invent the set of all k disjunction, right? Because I know that it's a k-CNF, so I care about disjunction of size k, and these are going to be my new features. So I know that there is only polynomially many things like this. So these are going to be my new variables. I'm going to call them y's here. And yj is going to be some disjunction of size k. Now, with these variables, all I have to learn is a conjunction. And you know how to learn a conjunction. Now, what has happened? There are two important things. I'm going to give you an example. So I started with n equal 4 variables. I'm assuming that k is 2. And I'm simplifying the problem to assume that I only have monotone case here and have no negations. No variables are negated. And this is what I'm doing. So these are the 6 new variables that I'm introducing. Okay? So I started with 4 variables. My dimensionality was 4. Now I'm taking all the disjunction of size 2. These are all the disjunctions of size 2. So I move from dimensionality 4 to 6. And you know how to learn it now, because it's just conjunction over this. Why do I mention it? Because, look at this. Let's assume that at the beginning I had these 4 examples. Now I'm moving to these examples. 6-dimensional examples. And you can check that this example translates to this example translates to this, and so on. The reason I mention it is because of one important assumption that we've made. We talked about distribution free earlier, and I said the definition of PAC learning is, I don't care what distribution there is, we should be able to learn. Now, let's assume you had a learning algorithm that only knows how to deal with uniform distribution. Okay? I'm arguing that this distribution that you got here after you change your feature space is not uniform. How do I know? Basically, what does it mean that it's a not uniform distribution? There are some examples that you'll never get. Give me an example of an example that I will never see in this space. Why?
Because if 1 and 2, either 1 or 2 is not on, either 1 and 3 is not on, and there's no way 2 or 3 on.
Yeah. So basically you're saying if this and this are off, it cannot be the this, or I think you mean the this is on. Think about it, right? If these two are off, this cannot be on. Which means some examples will never be observed. So if you had an algorithm that only knows how to deal with uniform distribution, once I transform the space, not going to work anymore. So that's another algorithmic significance of being distribution free. You want an algorithm that you can say something about for all distributions. Okay, so now I'm a little bit late, and given that we have a talk here at 3, I want to stop. So I'm going to tell you what's coming. What's important that I wanted to do today and I didn't get to is 2 things. One is, we gave a theory and you were concerned about the word consistent. So one thing I want to do is I want to get rid of consistent. Basically, I'm going to show you that the same theorem that we proved for consistent, we can state, I'm going to just state it for the more general case, where you look at the M examples, you're not completely consistent with them, but you're almost consistent with them. And we can still say something good about what's going to happen in the future. That's one. And 2, so far, everything I said, we had finite hypothesis spaces, right? So our bound was size of H times something. But what if H is infinite? Which in most cases it is, right? So when you work with linear separators, it's an infinite space. So we want to be able to take exactly the same theorem and say something about the infinite space. And it turns out that almost the same thing can be said. I'm going to replace size of H by some other parameter of H that will allow H to be infinite. So hopefully we'll be able to finish this in the first half of Tuesday. Okay, that's it. So see you Tuesday.
for the project, is it possible for us to use multi-threading? Like if we store all the weight vectors in a huge matrix and then separate to like several pieces at the end and then use multiple courses to run it?
You talk about the project?
Yeah, I was talking about project.
Say it again.
Because we now only tracking one cumulative weighted vector and a current weighted vector. So is that possible if I just, instead of doing a cumulative thing, instead I'm keep tracking each time we make a mistake, append the current weight to a matrix, and then at the end use multiple thread to calculate the cumulative vector.
Why do you want to do this?
Because it seems to be, it could be faster. That's what I'm thinking. Like, currently I'm using NumPy, so it's gonna take me like 5 minutes to
So
run.
basically, you want to develop a learning algorithm that improves over existing learning algorithms. That's a good thing. For the project, you have to read some paper. So at least to know that it's a valid idea or that people have thought about it before in the literature or something like that. So I think the closest thing that I have to what you're saying is really parallelizing the algorithm. And you can and this is a very important research direction that people are thinking about. Let me say what you said in a slightly different way. Let's assume that you have a lot of data. And I just cannot learn, I cannot fit it in memory, for example, or I cannot. So what I'm going to do is I'm going to split it. Or maybe, me and my cousin and my other cousin are going to learn separately, but then I want to merge it somehow. So how do I do that? So it's kind of a distributed version of the algorithm. So each one of us is going to keep your weight vector, but really I want to make predictions with the accumulation of it. So people have looked at that, and it's an important problem still today, both from the theory is rather well understood. The application, how to do this right, is still not complete. So there are some systems that are doing that, but most people don't use them because it's so if you can democratize this, I think it's a key contribution. So look a little bit about distributed learning, and if you want, if you can find anything, I'll give you some pointers. Yeah.
Thank you.
Why is this?
Here to there.
No, it's not for me. This is the output. This is the final thing. This is the step is this, and then I copy it. So it's not, how did I get to this? So in the power here, it's the number of disjunctions. The number of disjunctions is 2n to the k, approximately. It's 2n choose k. Because I have 2n variables really, and I have to choose k of them. 2n because it's a variable and it's negation.
Oh, I see.
So it's 2n and I have to choose k of them. So it's 2n choose k. You're familiar with n choose k?
Yeah, I will be.
You will be, okay. so then it's 2n choose k is something like 2n to the k.
Got it. Okay, well, it makes sense. And
No, I'm staying here. Because of the
can I ask you like?
Yeah, you can ask me.
About this one, about the proposer, like my opinion is thinking of doing like sentiment analysis, and we looked up some literature, and there, and then we also think about what like data we can access, and we come up with a trigger.
Okay.
So trigger and sentiment.
So it's your own data or someone else's data?
Someone else like.
Okay, that's fine. There is a lot of data available.
Oh really? Oh, cool.
Yeah, there is a lot of data available, annotated already.
Oh really?
I actually don't remember now off the top of my head Twitter data. I know of other data.
Oh really? That would be really great.
There is a lot of reviews data and so on.
Would you be able to make a post?
So do two things first.
Yeah.
Search a little bit.
Oh yeah.
search for sentiment, annotated sentiment data, you will see. So one collection, there is a Stanford University data set. It is very large, relatively large, on sentiments. And its reviews, I don't remember, is, hi. Oh, so you're coming to help us with the other second projector? Excellent, thanks. I don't remember if they have tweets, but I bet you will find also a collection of tweets. Drop me an email if you can find any, and I'll try to find something with tweets. Yeah, there is a lot. Almost any paper in the recent years that you find essentially, you will see the data that they always go for the Stanford collection, and then they have so look at some recent papers or something else, and you will see.
So is there a goal to develop a learning model or?
So I think, okay, so your goal can vary. Could be first reproduce results in the literature, and then maybe try to improve on them. It can be adaptation. So you train on one data set, and you want to, and then if you take your model that you train on one data set, you run it in the second one, your performance is going to drop significantly. Maybe you want to improve it a little bit to see how can you be more robust for the patient. So already you have two options, and you can do other. So you don't want just to run and compare learning algorithm because it will be boring. So you want to take this data, see what people have done, and try to do something interesting with this data. Either improve, as I said, or do adaptation and do something. Okay?
Thank you.
So anything for them?
I thought putting like
No, I didn't mention it at the end, but I was managing to see a mission. And I didn't get to it. So it's not good. So that will mean rethinking the I'm looking at it. Probably SCM will not be great.
Yeah. I didn't make. I guess what the questions are just like.
Yes, but yeah, probably will not be. I think otherwise it will not make sense. Even just in the open lecture. So.
Should we ask the question if that makes sense?
Yes, so 50 minutes and I'll do it with you. Definitely. But, it's very easy to keep the same because I'm not doing that. I'm developing. Basically, that's what is the concept, and understanding the marketing. But yeah, we will see how much. They just, I'm speaking to him, I talked to him 10 minutes ago. and he just came, so it's excellent, yes. This looks
Yeah, actually the color is better.
yeah. He just turned it on. So when I got, I still used it.
Yeah, I mean, I teach here, but it was.
No, but this is nice, I mean, it's a bit embarrassing. We have only one of them. For 34 or 1, more is ACL.
Well,
stage lights on. Should I just do all on or?
Shine this way or directly above?
Like this.
Because that's gonna wash this out.
You think?
Yeah.
Okay,
So
we can
that's,
do
so if you do,
Number 8 is the best.
Number 8 is the best. Okay.
so that was 8. See, this is what happens when you.
Okay, that's not good.
So this is, no,
Yeah, 8 is the best.
Hello.
I'm aware of that.
Back end there. Would be very good. So, we have both screens, right? We're good? and working?
Wonderful. I can point out.
I can be good. Okay.
Alrighty.
This works.
We actually.
Yeah.
That's the wrong way around. I hope it's that. I hope that's charged.
I can get,
Do you have a spare battery?
I can get spare batteries for it. I'll be right back.
Awesome. Speaking of charging.
Otherwise, I might have to end the talk exactly at 45 minutes due to time, due to battery constraints. And then I have to continue on the blackboard. Which is probably, I've never seen a job talk on the white blackboard, have you ever?
I've heard of it. I've never actually seen it. But I think that must be.
I don't want to be the first one to do that.
It's promising.
Aha! Everyone's happy. Now, let me get.
Did it cut off something? I think it's good, right?
Let's see.
Just maybe.
No, it's perfect.
Oh, it's good. Okay. 3 or 5. Okay. So yeah, you better not start early.
I need to make sure he gets what he needs.
Yep. 305 is still better than Germany, but we have the academic quarter. It's like we would do 315.
I can quiz them. Is that how it works? You come in late.
That's
you
right.
You get to answer questions. Perfect. Everything's working.